Welcome back. Today we are continuing our talk on kinetics. So last time we talked about linear kinetics, started introducing forces and Newton's laws of motion, inertia, acceleration, things like that. Now we are going to transition those laws into angular kinetics. So a lot of these will sound familiar as we go through, especially the laws of motion, because they will be very similar as to what the laws themselves actually are, but now we're going to take them into an angular world and talk about how each of those three laws of motion from Isaac Newton apply to things rotating as opposed to moving linearly. So for this lecture, again, we are getting into Newton's laws of motion in the angular analog. So we're going to revisit inertia from an angular perspective. We're going to talk about acceleration and angular forces causing those accelerations. And we will revisit the law of action, reaction from an angular perspective as well. Along the way, we'll also talk about angular momentum. And in this lecture, we're going to talk about how that conservation of momentum principle that we mentioned in linear kinetics is really going to be a major driving force in how we create and produce a lot of different types of human motion. And finally, we will talk a little bit on lever arms, what they are, where we see them, and the benefits that they provide for us and the advantages that they provide for us as well. Now, to get us started, a little bit of a thought experiment for us just to introduce. So what we have here is an example, and in the picture we've got a baseball bat example. I have a golf club. For you at home, you can use any number really of things as long as it's some type of non-uniform object. So if you have a bat, if you have a golf club, if you have a racket, it could even be a broom or a mop or a Swiffer, anything with some type of handle that isn't perfectly uniform. Okay, so meaning one end is heavier than the other end. Anything like that will work for this. And what I would like you to do is we're going to create an angular motion with this object while holding it in three different places. So once you've got the object found that you want to use, you're going to hold it first all the way down at the lighter end. Okay, so if it's a baseball bat or a club or a racket, you're going to be holding it down at the bottom of the handle. I want you to hold it out in front of you with one hand, like that, and you are going to create an arc with it, just rotating it down the horizontal, back, stop it, back, and just create these little kind of half circle motions, stopping it each time you get about horizontal. And I want you to feel what that motion is like. If it's hard to stop when it gets to the bottom, what it's like to change the direction, what it's like to control that motion. Once you've got a feel for that, we're going to go to our next position. So just choke up to about the halfway point of your object. Okay, somewhere, it's not super particular, somewhere around the middle though of your object. And do the same thing. Okay, and rotate it back and forth the same way. And get a feel for how that motion is, what it feels like. Once you've got that, lastly, I want you to go all the way down to the other end. So you're basically holding it now upside down. So I'm right down at the bottom, just at the head of this glove there. And I want you to do the same thing now. Rotate it back and forth, these little half circle motions. Again, gauging how that feels. What is it like to stop it? What is it like to change its direction? And rotate it back and forth. Now, once you've done that for all three positions, I want you to ask the question, which of those positions that you held it, was it the easiest to rotate back and forth? So you rotate it down, stop it, change its direction, rotate it back. Which one felt easiest to do that? Which one was the hardest to do that? And which one was kind of in the middle of your object? And as you think through that, hopefully, depending on the object you selected, everyone should come to a pretty similar conclusion. That being, the hardest method should have been all the way down at the grip. So all the way down at that lighter end. Usually the easiest one is all the way at the other end of the object, and then the middle is in the middle. It's easier than the first, but a little bit harder than the second. Okay? And so that brings us to an important principle in angular kinetics, and it's the title of this slide. We're talking about a concept and a term known as the moment of inertia. And so in our last lecture, we introduced inertia, and we introduced it in objects at rest, where it was quantified purely by the mass of the object, so how much it weighs, how big is it. Then we talked about things moving linearly. That's where we introduced inertia being quantified as something's momentum. So then it was the mass of the object and the velocity of the object. So how big is it and how fast is it going? Now we have a new term known as the moment of inertia, or MOI, and that is our method of quantifying angular inertia. So the moment of inertia is how we're going to quantify how hard it is to move or change the state of motion of something moving angularly or rotating, which is what you were doing when you're rotating this object back and forth, because you're having to create that motion, stop it, changing its state of motion, rotate it back the other way. So you're just stopping and starting this angular motion over and over and over. And this term, moment of inertia, is what dictates how hard that felt to do. Okay, so let's talk a little more on moment of inertia. So moment of inertia is the angular version of inertia, and it gives us an idea of how hard it will be to rotate an object or stop an object from rotating. And it is represented by the letter I, so capital I represents moment of inertia, and the equation for it is I, moment of inertia, is equal to mk squared. And so what that is the mass of the object that we've talked about already, and then a new variable, k, known as the radius of gyration. Okay, so the radius of gyration, that is a new term for us. Let's talk about what that is. The radius of gyration is a distance measurement. Okay, so it's a length measurement. It is the distance on an object from the axis of rotation of the object to the center of mass of the object. Okay? That's the radius of gyration. It's the distance from the axis of rotation, which in this example is where you are holding the object. So when you're holding it down at the bottom, that's your axis of rotation. You choke up to the middle, that becomes your axis of rotation. So it's where you're holding the object in this example. To the center of mass. Okay, so for a non-uniform object, something like this, we know that the center of mass is going to tend to be a little closer to the heavier end. So you can find that on whatever object you have, find that balancing point, and that point will be the center of mass of your object. So right about there is the center of mass of this golf club. So what we're talking about for the radius of gyration would be where I'm holding it. If I hold it all the way down here at the end, the distance from that hand to this point, the center of mass. And that distance represents the radius of gyration. Okay? And again, moment of inertia, the two things that make it up are the mass of the object and that radius of gyration. So really what we're talking about with this equation, kind of in layman's terms, is how much the object weighs, how big is it, and then how the mass is distributed on the object. Okay, so about where most of the mass is on the object. And that's really going to be the main players that dictate how hard it was for you to rotate your object. Okay. Now, considering that, again, think back to what was harder to do of those three examples. Down here, we said was pretty much the hardest one. And if you think about that, that one has the biggest radius of gyration, which means when you plug it into this moment of inertia equation, it's going to be the highest one. So it's going to have the biggest inertia, and it's going to be the hardest one to rotate. When you choked up to about the middle now, you change the axis of rotation, and because of that, now the distance from axis of rotation to that center of mass got a lot shorter. Okay, so that means the radius of gyration went way, way, way down, which means the moment of inertia is going to go down because the mass of this club didn't change. It didn't change the weight of this club, but that radius of gyration went way down. Okay. When you came to the other end, holding it there, you got even closer to that point, depending on the object you chose and where that center of mass was. And so that radius of gyration got even shorter. And so the moment of inertia is the lowest there, making it feel easier to rotate. Okay? And so when we choked up and we changed the hand position of the object that we were holding, we were actively changing where the axis of rotation was on an object, and because of that, we are altering that radius of gyration, again, the distance from axis of rotation to that center of mass of the object. And that made it depend whether this felt pretty easy to rotate or harder to rotate, okay, based on moment of inertia being manipulated. So one of the common places you'll see this pop up a lot in sporting terms, especially in kind of warm-up settings, is if you're watching baseball and you see someone in the on-deck circle, so they're warming up, so they're getting ready to go up to bat. And generally what you will see with a lot of people, not everybody uses them, but a lot of people do, you will see them put the big plastic ring on the end of their bat. It's called a donut. Essentially, it's just a big, heavy piece of plastic that wedges on the end of the bat. It makes it harder to swing. And the question is why? Okay, so why do they do that? A couple things are at play here. Number one, if we put a big, heavy thing at the end of the bat, number one, it's going to increase the mass of the bat. If we go back to moment of inertia, increase the mass, moment of inertia is going to go up, harder to swing. Additionally, if you put a big heavy piece of plastic down at the end of the bat, that's going to shift that center of mass closer to the end of the bat. So it's going to push it even further away from you, which means if you're just holding it down here like normal, not only have you now added more mass to the bat, you've shifted that center of mass further away, increasing that radius of gyration. So both factors involved in the moment of inertia have been increased. So you put this on, do your warm-up so that the bat feels harder to swing. That way, when you take that off and actually go up to the plate to swing, your bat feels lighter and easier to swing. Now, there's a lot of research out there of does this work, does this not work? It's pretty conclusive at this point, especially at the elite levels of baseball, that this doesn't really actually affect the actual swing mechanics that much. But there might be some evidence of stuff affecting it psychologically in the warm-up protocol that it could help there. But as far as affecting swing mechanics, it doesn't seem to provide that much benefit. But it's a fantastic example of where you see this moment of inertia manipulation come in a real-world sport setting, of you trying to make this feel harder to swing just by adding the mass in a specific location on the bat. Now, we introduced in the last PowerPoint momentum, specifically then linear momentum. Now we are introducing angular momentum. So angular momentum is represented by a capital H. Remember that linear momentum, again, was mass and velocity of an object. Angular momentum, quantified, is I, moment of inertia that we've just introduced, multiplied by angular velocity. So it's similar to the linear version. It's still the inertia equivalent, mass and moment of inertia. and the velocity component. So we have linear velocity and now angular velocity. So again, angular momentum quantified by the moment of inertia and angular velocity. Those two components are going to be important for this angular momentum principle. We're going to talk about this more in just a minute. First, let's take a step back and revisit center of mass. So I know y'all have done a lot in lab with center of mass and calculating the center of mass and a lot of stuff with the math components of it. I want to take a step back a little bit and talk about it a little bit more in layman's terms of the center of mass. And so when we talk about what it is, okay, as generically as we can, it's the average point of where all the mass is of an object. It's that balancing point, the collective average of all the mass of an object. Okay. So if we have something that is perfectly uniform, such as the ruler example, that center of mass for that object will be right in the center, okay, because the mass is perfectly distributed. So that center of mass right in the middle. If we have a non-uniform object, like a club, a bat, a racket, a body segment, whatever it might be, that center of mass will be closer to the heavier end. Okay, so it won't be right in the middle. And an important example here to note, for something like the donut, the center of mass is actually in the center of the donut. Okay? So, what that represents for us in an important note is that the center of mass of an object can be outside of the object itself. Because for the donut, it's in the actual hole of the donut, which isn't actually physically part of the donut. And that can happen in humans and animals as well. Okay, and that's potentially important for us moving forward. Now, these centers of mass that we're talking about here, they're not going to change unless we actually physically change the object themselves. Where we can start to get into some fun parts of this is when we start to connect things together. So connecting pieces together, body segments together, whatever it might be, and have a collective average. Okay, so let's talk about what we mean. Here you have three orientations of an object. So you've got two smaller pieces, so these kind of blue rectangles, these blue bars are going to represent a segment. The little circles on each one represent the center of mass of each individual piece, so their center of mass, that's not going to change. And then you've got the big circle, which is going to represent the collective center.